Hello, everyone. Let's begin the snack session. The first talk is the first security of FRI and the related snacks. This talk is given Alexander. Welcome.
Hello. Thank you very much. Yes, my name is Alex. I'm happy to be here to present our work. This is joint work with Albert Beretta, Jonathan Cass, Justin Fowler, Ratush Ranja Tawari, and Michał Zając. If you're Polish, please forgive me, I cannot pronounce that. Okay, so today's topic is SNARKs, which stands for Succinct Non-Direct Fragments of Knowledge. If you're unfamiliar with what these are, just very briefly, they are protocols between two people, a prover and a verifier, with respect to some fixed language L and a P, let's say. Let's say L is the language of circuit satisfiability, as an example. And the verifier would like to know, hey, is this circuit satisfiable? Is X in this language? A prover can come along and say, yes, I know a witness that shows that this is true, and it'll give a proof pi to try and convince the verifier of this fact. The verifier then examines this proof and then decides to output accept or reject. We always want some standard properties, completeness. For every valid input witness pair, the verifier should accept an honestly generated proof. Some epsilon soundness property, if you have a non-instance, for example, the circuit's not satisfiable, then no matter what a cheating prover, in this case computationally bounded, does, you can't convince the verifier to accept except with properly most epsilon. We also want knowledge soundness, which means there's some extractor such that for any instance X and any prover algorithm, this inequality is satisfied. You can basically extract it. So how do we build SNARKs? A common paradigm that has become very popular is, we also want succinctness. Of course, the prover can also send the witness W, but that can be very big. Think like the circuit is huge. So you want the proof pi to be little o of the witness size and ideally logarithmic gradient. Right, so how do we build SNARKs? A common paradigm is to first build what we call a public coin interactive oracle proof for the language. So we still have the same picture, prover and verifier. Now the prover is computationally unbounded, and they perform some interaction more than one round, where the prover is going to send an oracle F1 that the verifier can query at any point it wants for free. And you repeat this some number of times R, and the verifier each time gives a random challenge CI uniformly at random that doesn't depend on any secret state or any messages that the prover sends. And then some final oracle is sent. And then the verifier is going to query all these oracles. It's going to do some computation. It's going to output accept or reject. And we always want the same complete soundness and knowledge soundness properties. So step 2 in this paradigm is you then replace all your oracles with Merkle roots. You introduce some random oracle for simplicity. Then you Merkle hash each of these oracles. You can think each oracle is just one big long string over some domain, and then you can hash it to a Merkle root. And then rather than the verifier querying these oracles, because now it has Merkle roots, it asks the prover to give it Merkle authentication paths to prove that a oracle F1 at point 1 is equal to some value. And the verifier additionally checks this. And then finally, using fiat Shamir, we remove all of the verifier interaction with a hash function. So each of the random challenges sent by the verifier, C1s up to CR, are now replaced with correctly hashing the messages of the prover and the instance X. So the crux of this talk is on the security of fiat Shamir, and unfortunately, it's not secure in general, even in the random oracle model for many round protocols, where many rounds here means more than constant number of rounds. And there's a lot of attacks, like even sequential or parallel repetition of a constant sound interactive proof, which would lead to, let's say, negligible soundness, is not necessarily secure under fiat Shamir. There are attacks against this. And even still, people still apply fiat Shamir to many round protocols anyways, because removing interaction is useful, interaction is expensive in practice. And a lot of these systems, let's say in SNARK world, often only prove interactive security, then heuristically apply fiat Shamir without any other consideration. So what do we do in this work? We zoom in on one such protocol called the FRI protocol, and we actually prove the fiat Shamir security of this protocol and a variant of it called batch FRI. I'll get to what these are in a bit. And then this fills in some security gaps in prior work, which assume that FRI has some fiat Shamir security properties without actually proving it. We also introduced a notion which we call delta correlated IOPs and prove their fiat security. And intuitively, these are just protocols that use Fry as a subroutine, and I'll talk more about that in a bit. And then we finally formulate a delta correlated IOP, which captures many protocols in practice, which we call Plonk-like, and we also prove the fiat security. This captures a bunch of systems in practice, and some other systems can be retrofitted into our framework as well. And here, Plonk-like roughly refers to protocols that use Fry plus some permutation argument, and we call it this because it's popularized by the Plonk structure. Okay, so for some context, why do we care about Fry? What's popular? Here's a screenshot from L2Beat, which is money being moved around on layer 2 Ethereum transactions. And the top three all use Fry at various levels of conjecture security, interactive security. And this is about $600 to $700 million being moved around at interactive security levels, rather than fiat Shamir, rather than choosing parameters based on fiat Shamir security. And also, Plonk-like protocols are used in a lot of layer 2 projects as well. And before this work, really no formal security analysis for Fry under fiat Shamir existed. So I'm going to tell you a bit about what the Fry protocol does, not what it quite is yet, because you don't need to know that for the theorem. So it's parameterized by some finite field and some specific subgroup of size 2 to the n. Don't worry too much about the specific properties we need. It has some degree bound to the k, and it operates over the space of read-solvent code words, which is just the set of all polynomials of degree at most are restricted less than d0, evaluated on the domain L. Okay, so these are just 2 to the n length field vectors. And then it has some rate parameter, which we define like this, some proximity parameter, which will become apparent in a second what it does, and some verifier repetition parameter. So what Fry does is say, if you have a function g0, it proves that you are delta close to this space of read-solvent code words. That means you agree with some polynomial in the space on at least 1 minus delta fraction points. Okay. Now, for fiat Shamir security, there are many notions to prove this, and we choose round-by-round knowledge soundness. So round-by-round soundness has the following intuition. If you start with a false statement, like x is not satisfiable, then intuitively any protocol that the prover tries to engage with you, the verifier, it should be doomed. Like the prover shouldn't be able to convince you that this is true when it's not. And no matter what the prover does, the protocol should remain doomed. So during every round of the interaction, the prover is trying to convince you that this false statement is true, and it shouldn't be able to flip the protocol state into a case where the verifier believes this is true. A bit more formally, protocol pi for language L has round-by-round soundness epsilon. If there's some doomed set of transcripts such that, well, this is what I just said, if the protocol starts in a state where x is not satisfiable or not the language, then the protocol should just be doomed without anything happening. No transcript, empty transcript, nothing should be able to get you out of this. Then if you have a complete transcript, if the protocol is doomed, intuitively the verifier should just reject it. It shouldn't be convinced by what you said. And then this third property is the round-by-round part. It's this kind of inductive assumption. Suppose you have I minus 1 rounds of interaction, and during this interaction, you end up in the doom set. Then, no matter what the prover sends, so for all prover messages, over the probability of the verifier messages, you should not be able to leave the doom set, except for probability most epsilon. So again, with probability at least 1 minus epsilon, and if epsilon is negligible, you will forever remain doomed. Okay. And the important thing, as I said, round-by-round soundness implies fiat Shamir security. So specifically in the random oracle model, because that's what we care about in this talk, for Q query adversary and K bits of output, if you have round-by-round error epsilon, it implies fiat Shamir security error Q epsilon plus what's basically the birthday bound for finding collisions in the Merkle trees and the hash function. Okay, now I can throw this theorem on the board and tell you to look at it, and this is what we actually prove. We prove the round-by-round soundness of Fry, and it will become apparent what these two terms mean. So everything setting up the theorem just says if you start with a function that is delta far from this read-solvent code space we specified, then the round-by-round soundness error is the max of these two terms. Looking ahead, it's the max of the first term, which corresponds to some first phase of Fry, and then the second term, which corresponds to the second phase of Fry. And I'll talk about that. And the same results hold for the batch Fry protocol. I'm not going to get into details. You need a batch with distinct challenges. I'm happy to talk about it after the talk if you want to hear more or read the paper for details. And by the previous slide, this implies fiat-trigger security in the random. So how does this compare to the best provable soundness bound for interactive security? So interactive security of Fry looks something like this. Epsilon1 was our first term, epsilon3 was our second term, and there's this other additional epsilon2 term that doesn't come up in the Rambo-Rand soundness analysis. So we prove it's max of epsilon1 and epsilon. Okay, so moving on, the second thing we do is introduce the notion of delta correlated IOPs. So here we have the IOP picture. To make it delta correlated, we introduce an additional constraint which says all these provable oracles are delta correlated with some Reed-Solomon code space. So each oracle is delta close to some fixed Reed-Solomon code space at the start. In addition, the verifier is given an oracle for checking this delta correlation among all of the functions. And so the additional step involved in this kind of IOP is the verifier will use the oracle O to simultaneously query and check that all of these oracles are indeed delta correlated. So this gives us a nice tool for building protocols. So suppose I have a delta correlated IOP for some fixed Reed-Solomon code space, okay? The first point here says, suppose I have Rambo-Rand soundness error epsilon when delta equals 0. So in this case, the prover is actually constrained to sending low degree polynomials to the verifier. So in the delta equals 0 case, in this protocol, the prover has to send Reed-Solomon code words. So if you have Rambo-Rand soundness here, it implies Rambo-Rand soundness for any delta bigger than 0 under this constraint delta equals this term. So you can choose beta being whatever you want in this thing, and you get Rambo-Rand soundness basically for free with this plus. And then second, if you have a protocol pi prime, which actually does the delta correlation testing, you can replace the oracle O with this protocol. And if the protocol pi prime had Rambo-Rand soundness error epsilon prime, then you again have Rambo-Rand soundness error, the max of the first term we saw and the second term. So this gives a really nice new way to build smarts. So you construct a Rambo-Rand knowledge on zero correlated IOP. This is again where the prover is restricted to sending low degree polynomials in the Reed-Solomon code space. And arguably protocols fitting this are much easier to construct. By our theorem, you can then transform it into a Rambo-Rand sum for any delta bigger than 0 under the constraint that the previous theorem right here. Then you can replace the oracle O with an IOP for delta correlation. In this case, Fry is such an IOP with our new theorem, and you get a Rambo-Rand knowledge IOP. And then you can use a variant of the fiat-Schubert transformation that gives you a spark. So it's a nice new parameter. And then finally, we present a new delta correlated IOP, which we call a Plunky, and it captures many Plunk-like protocols in practice that use Fry as a subroutine. We base it off of the Plunk E2 system. We then prove Rambo-Rand soundness of this protocol. And then our results can also be used to obtain Rambo-Rand soundness of the ETHSTARK protocol and the RISC-0 protocol. But ETHSTARK has also since been independently proven to be Rambo-Rand sound in their write-up on ETHSTARK. Okay, so with my remaining time, I will give a full overview of the Fry protocol and then tell you how we get Rambo-Rand soundness. So phase one of the Fry protocol has two phases. So the first phase is what we call the folding phase. In the original paper, they call it the commit phase, but I think the folding phase is a more natural name. So we have our prover and verifier, and the prover is saying, hey, I have this function, and I'm claiming it is in the space of Reed-Solomon code words. So it sends an oracle to this function, because this is the interactive oracle proof, and the verifier sends some random challenge. Now what we're going to intuitively do is fold G0 into a new polynomial G1. By the special properties of L0, you can define this new subset L1, and it's going to have half the size of L0. It's just going to be all the squares of L0. And you define a new degree bound, which is half of the previous degree bound. So now G1, I'm not going to tell you exactly how you define it because it's complicated and you don't need it for this talk, but intuitively what you're doing is you're taking an alpha linear combination. You're kind of taking the left half and the right half and you're using alpha 0 to fold them into each other to make a polynomial of half the degree. And then you're going to recurse on this new polynomial, if it is a polynomial, and this new Reed-Solomon code space defined over the new domain and degree. So you keep doing this, keep doing this, keep doing this until you do it k times. So log is 0. And now you have a degree bound equal to 1, which means that the prover should only be sending constant polynomials. So you have all these, the verifier has all these oracles, and then in the final round, this is what we call the query phase. The prover must send some fixed field element, and this is actually very crucial for soundness of the protocol. Even though the domain might be still larger than 1, this is a constant degree polynomial, so you can just, or sorry, this is a constant polynomial, so you can just send what that constant is, and this is key. Now the verifier is going to check consistency. It's going to query each oracle it has at 2 positions, and it's going to check pairwise consistency of all these oracles. Based on the folding definition, you can get away with it by querying 2 positions at everywhere. You can check everything, and then you repeat this L times. Okay. So now we get to the round-variant soundness. So first, you can look at the round-variant soundness of the folding phase. And of course, if the protocol starts doomed, the protocol starts with a false statement, right? This function is delta far. So you start doomed. You're already doomed by definition. And now I have a prover here who's trying to convince you otherwise. This is in fact a Reed-Solomon code word it's saying. And unfortunately here, even though it might seem a little weird, the prover's hands are tied in sending the actual correct polynomial. If it sends something different that is delta close, then you're already in the true case. Or if it sends some other G0 that's delta far, that's fine also. And often in practice, the prover gets this function from something else and doesn't have control over it. So the intuition here is that when you look at round-variant soundness, you can try and think, in what situation would the prover not have to do anything anymore? The prover could behave honestly, and then the protocol would accept it. So in this case, G1, if G1, the correct folding, is delta close to the Reed-Solomon code word space, then this malicious prover can actually just behave honestly. It doesn't have to do anything. And then it would convince the verifier. And then by prior work, the actual probability this happens is this term here. This is the first term from our round-variant soundness error. Okay, so now we get to the inductive phase of the round-variant soundness proof. So we're in round I, which starts doomed. And for simplicity in this talk, I'm just going to assume that this gi minus 1 is correctly computed, and it's also delta far. So this prover is going to send some function, gi star, whatever that is. And then we're going to say the protocol is doomed if and only if one of 2 things happens. If this function is not correctly computed from gi minus 1, because you can send something arbitrary here, or if the next polynomial that you're supposed to compute based on the honestly computed gi is delta far. Intuitively, what does this capture? So first off, if you send something that's not correct, basically what will happen, not a correct folding, basically what will happen is during the query phase, you'll get caught with high probability. So if the prover does this, it's kind of screwing itself in the end anyways. And then here, if the actual correct computed thing is delta far, the prover also will get caught. So these are intuitively the 2 cases that happen. And again, by prior work, this happens with this probability. Then in the final round in the query phase, we start doomed, which means at least one of these functions is delta far, not including the original function. And then still again here, the prover's hands are tied. It has to send a fixed element of the field. This is what the verifier expects, and it needs to send this. And so now it's really simple. The protocol is not doomed if and only if all verifier checks pass, because then the verifier would accept, right? And by prior work, it's actually the case if any one of these are delta far, then the probability all the verifier checks pass is this quantity here, 1 minus delta. Intuitively, you should think of 1 minus delta fraction of the points they agree, and the probability you land in that is 1 minus delta, and you raise it to the power L, so you push it really far down. And that's really it. That's the round variant soundness of Fry. And so again, at a bird's eye view, we proved the round variant soundness of Fry. We filled in some security gaps of prior work. We introduced this notion of delta correlated IOPs that gives you a new way to construct snarks. And we formulate in practice, we formulate delta correlated IOP, which captures many protocols in practice and preserves security. Didn't get into the details, not enough time. And that's it. Yeah, thank you very much.
Thank you for this great talk. So could you back to the previous this next? Yeah. And so my question is, how does the Wi-Fi tell that this the code word is delta var, because it only gets one point from the code word. It's only text that it's not specific coding.
Yeah. So basically, the consistency check, there's an expected thing that should happen. So you can think of two cases. If the prover sent something that was bogus, then with high probability you're not going to get a correct folding, and this check you perform will get caught with this much probability. Or the prover behaved honestly during everything, and you still end up with something that's delta var. This condition here then gets you caught, because if you are not close to a low degree polynomial, the last folding won't be a constant degree polynomial. Or sorry, it won't be a constant polynomial. So there's going to be points where it differs, and the folding will be incorrect.
How do you rule out this situation where the prover gradually changes one position in each round, and finally it somehow succeeds in creating a valid token in the last round?
It's captured just by this. Like, you can think of this function as arbitrary, and it's exactly what you expect. It only differs in one place, and even then it doesn't matter. You'll still get because in the end it's going to be like the folding will not match up.
But if you only change a single position, how can you catch it?
Right. So I guess the key thing here is if you're changing the single position and you're still delta var, it doesn't matter, right?
Okay.
Like, changing a single position isn't if you change a single position and goes from being delta far to delta close, that still is captured by the analysis.
Yeah. I see. Thank you.
Yeah.
Any other? Is this all soundness, or it's proof of knowledge?
It's both. So it is this proof is for both round by round soundness, and like with additional work, you show the same bounds hold for round by round knowledge soundness. And yeah, so you get round by round knowledge soundness as well, which gives you knowledge sound, which actually gives you the snark part.
Yeah, two questions. So one was that you showed these two theorems. Are those compilers? Like, do they actually change the protocol, like to go from a zero correlated IOP to a delta correlated IOP, or is it just you show that any zero correlated IOP somehow is a delta correlated IOP?
I think the second one, I have to double check, but I'm pretty sure it's if the zero correlated version is round by round sound, then the delta correlated one is also round by round sound. I think it's a reduction that just says that you can break the second one, then you can break the first one. I have to double check. I'll get back to that though.
And then the other question is that in practice they do this thing where they grind the challenges.
Yes.
And yeah, basically you have to select the challenge which starts with a lot of zeros. Did you analyze that, or?
So I'm going to take that and expand on it a bit. Fry does a lot. People who using Fry in practice do a lot of things to optimize Fry, like folding more than in half and doing grinding. So in the case of like folding more than in half, this actually increases the soundness bound. Like, this makes it worse. And this is kind of the best case analysis for Fry. The grinding, ETHStark actually has a nice theorem in their write-up for this on how grinding affects the soundness of the IOP. And basically grinding is you have to, at the end of the fiat thing, you have to do a k-bit proof of work or something. And so that actually does increase the soundness at the end. And basically you should think of, like for example in Fry, if you have k-bits of grinding, the second term in the theorem, the 1 minus delta L, gets multiplied by 2 to the minus k. That's how grinding affects it.
Okay. Any other questions? We have no questions. Yes, the success speaker in.
Thank you.
The next talk is a recording talk. The title is Paradox, Knowledge Sound, Commit and Proof Ducks. This talk is given by Hilger.
I know. Following is a presentation of Malaysia that shows that the different concept on Blackbox, knowledge, sound, commitment, proof, snarks. My name is Asiacrypt. I come from Estonia. Let us first remember basic principles of non-interactive ceremonial arguments. An argument usually has a prover and a verifier, where both prover and verifier have access to a public statement X, and the prover additionally knows some private witness W. Knowing this witness W, the prover aims to convince the verifier that some property holds about X. For example, X is a satisfiable circuit. To convince verifier, prover sends a short argument line to the verifier. More precisely, an ASIC has to satisfy a number of properties. First of all, it has to be complete. Then it has to be sound. Then it has to be zero knowledge. But it can also satisfy a number of additional properties. For example, if the argument is short, then an ASIC is usually called a SNARK, succinct non-interactive argument. Moreover, if the argument satisfies knowledge soundness, that means that honest verifier does not accept if P does not know the witness, then the snark is called a snark. There's a very famous possibility result about snarks by Chilcher and Twix. Thanks to this result, every snark paper ever claims that their paper uses non-falsifiable assumptions or random oracle model due to the impossibility result of Chilcher-Twix. So what does Chilcher-Twix say? Basically, it balances four different desirable properties of snarks. First of all, the snarks should be adaptively sound. Second, they should be succinct. Third, they should be for hard languages. And fourth, they should be based on falsifiable assumptions. Chilcher-Twix said, or their paper said, that you cannot achieve all four properties at the same time. An important question is to understand if this result is typed. It is known to be typed in three aspects. So in each aspect, you know that three of the properties can be achieved, but one cannot. For example, the very classical result says that you can achieve the other three properties, but the argument is going to be non-succinct. Similarly, you can achieve other three properties, but the argument is going to be based on non-falsifiable assumptions. Until lately, it was completely unclear if Chilcher-Twix is also typed in the fourth aspect. That is, can it be proven, or can one construct a construction that achieves the last three properties but satisfies a weaker version of soundness, by which people usually mean non-adaptive soundness. There has been some progress in this field in the last few years. First of all, in Asiacrypt 2021, we showed that chain to X is indeed tight. That means we can achieve the last three properties, but the soundness is going to be non-adaptive. Moreover, our construct was a snark, which means that we didn't satisfy Morse soundness. In this year, Antonelli and others had a paper where they showed that this not achieving knowledge soundness was actually the best possible, in the sense that one cannot achieve the last three properties and at the same time have a non-adaptively sound snark. Their paper had also a positive result, which said that you can achieve basically the same properties that we achieved in the Asiacrypt 21 paper, but it was for a much smaller complexity class. Now, this might seem weird, why they proved this result, but the real reason behind that is that our Asiacrypt 21 paper has a flaw. Our construction there doesn't work. This was known to me, unfortunately, already 2 years ago, and in this paper we show why it is indeed the case. To try to correct this paper, we define a new soundness notion, semi-adaptive soundness, and we prove that one can achieve the last three properties, but the cost will be that the snark will be semi-adaptively sound snark. That is, it will be knowledge sound. This is, however, a new notion of adaptivity. And we still don't know after this work if one can construct non-adaptively snark that satisfies the last three properties. Antonelli, etc. showed that it cannot be snark, but maybe it can be a snark. We don't know. So we have a new construction and we need an open question. The interesting thing is that this is also a question whether one can separate snarks and snarks. Let us now recall what is adaptive soundness. Here I'm going to talk about adaptive commit and prove snarks, in which case the trusted third party first sends a CRS to the prover. The CRS can contain a commitment field, and it usually does. The prover, after that, constructs a statement and an argument and sends those two values to the verifier. In most of the cases, the argument contains the commitment to the witness. Because here X and Y are set at the same time, there's no fundamental difference whether the commitment is a part of the statement or the argument. And thus we can think of it as being a part of the statement. And thus we usually get the commitment proof snark or snark. The next classical adaptiveness notion is that of non-adaptive snarks. With those snarks, the prover first sends a statement to the verifier replies with a CRS, and the prover sends the argument to the verifier. Since the statement is sent before the CRS, the statement cannot contain the commitment to the witness, and thus the snark cannot be commitment proof. Let us next explain what is black box extraction. Black box extraction is very well understood in the case of interactive protocols. Let me give an example of signal protocols. In a soundness proof of a signal protocol, the prover sends the first message to the extractor. The extractor then chooses a random second message and obtains the third message from the prover. After that, the extractor invites the prover and sends a new random second message, C prime, that is different from C to the prover. And after that, prover sends another third message to the verifier or the extractor. And the requirement is that if both transcripts of the protocol are accepting, then the extractor can extract the digits. And indeed, it's very well known how to do it in the case of any secure signal protocol. It is much less understood how to achieve black box extractability in the case of music. You can imagine that the prover starts by sending a statement to the extractor. Extractor sends CRS and maybe some other information to the prover. Prover replies with an argument. Then the extractor reminds the prover and sends a different CRS to the prover and gets back another convincing argument. Intuitively, we would like now the extractor to be able to output the witness. Unfortunately, this is not so easy. Let us see more precisely what happens in the case of non-adaptive snarks. So, as said, in the new non-adaptive snarks, first the statement is sent, then the CRS, and then the argument. Intuitively, it can be shown quite easily that extraction is going to be impossible here. So what's the intuition? The intuition is that the prover can use a different witness in each rewind. And there's not enough rounds to build a contradiction, because there are no public parameters sent before X is sent. The prover cannot commit to the witness, and thus the prover is free of using a different witness in different cases or different rewindings. I must stress here that this is only an intuition. This is definitely not a proof. And Gentry-Wicks and the paper of Campanelli prove impossibility by using that sort of fact that the proof is succinct. Nevertheless, it is an intuition that we are going to build on. One more thing here is that in our Asiacrypt 21 paper, I would say that our paper is mostly correct, but we made a crucial mistake at some point that is not so easy to see, where we just assume the prover uses the same public. Now, this assumption is not true, because we did not enforce it somehow, and we also didn't use the fact that the prover uses different witnesses to build some like a contradiction. To solve this solution, we somehow need to add more rounds. So welcome to our second contribution, which is the definition of a new soundness notion, which we call semi-adaptive soundness for commitment proof snarks. In this soundness notion, the trusted third party first sends a commitment key to the prover. The prover replies with a statement and with a commitment to the witness. Then the trusted third party sends CRS to the prover, and the prover sends an argument to the verifier. The main reason here why we have this new adaptive notion is that we have more rounds. So we have more rewinding points for the black box extractions. In particular, we send the commitment key before the statement in the commitment. This means that commitment can be a part of the statement. Let us give now a very brief introduction to the knowledge soundness proof that we have. In this proof, the extractor first sends the commitment key to the prover. The prover replies with a statement and the commitment to the witness. The extractor now does the following many times. It rewinds the prover, sends to the prover a new CRS, and gets a new argument. More precisely, there's going to be one rewinding for each wire of the circuit. Each time the CRS is reprogrammed, and more precisely, the CRS is somewhere extractable. This means that during the ith rewinding, we can extract from this argument the neighborhood of the ith gate. The next step in the knowledge soundness proof is going to be as follows. Namely, if the prover used two inconsistent witnesses, we extract two inconsistent wire values. But those wire values both have been committed to by using the same commitment. And our insight here is that the commitment is going to be a vector commitment. So from different opening of a single wire, we can construct the contradiction. We construct an efficient, semi-adaptively sound commitment proof smart unit that is really practical. Other contributions of the paper are breaking the old paper, defining the new knowledge soundness notion, building several new tools like the new vector commitment scheme, and also the new proof technique. Getting the practical constructions on nature hassle requires several new insights and tools. Also, it is possible to use the classical construction of billion in this case, but this is going to be utterly practical, and nobody's probably ever going to implement it, especially because it uses PCP. Unfortunately, we don't have time to discuss this construction almost at all. Still, a very high-level overview of QNIC is as follows. First, the trusted third party sends a commitment key of the vector commitment scheme to the prover. Prover replies with a statement and a vector commitment to the witness. The trusted third party now sends to the prover the CRS, and crucially, the CRS contains the commitment key of a functional somewhere extractable commitment. Finally, the prover sends to the verifier the argument, where now the argument contains the functional somewhere extractable commitment to the witness and to the openings of the vector commitment scheme. For this to work, we have to design a new vector commitment scheme that basically is FSC friendly. I will not be able to define it here. the very high level idea is that we will have a vector commitment to the vector of y values, and we will have a summary extractable commitment to the vector of y values and to the vector of vector commitment openings. And the intuition is that if there does not exist a witness satisfying all gates, then there exist two gates, I and j, such that I use different values of some wire that is in the common neighborhood of both gates, at least for one wire. After that, in the knowledge sumness proof, we use the somewhere acceptable commitment to obtain two contradictory wire values together with corresponding vector commitment openings. And then we use the values, contradictory values together with the openings to break the position binding property of the vector commitment scheme. Here is a bit of example that what you need is two gates that share a wire that might have contradictory values. We use several tools here, and not all of them are well known. The first one is functional somewhere acceptable commitment that can be based on VDH. The second one is bilateral subspace causative active music that can be based on S and H. The third one is a new FSC friendly vector commitment that we propose in the current paper, but which is partially based on existing schemes. And the final component we need is a relatively new assumption that was proposed by us in 2021. The main security theorem of our paper states that if those three tools are secure and this fourth assumption holds, then our construction is semi-effectively computationally with special solves. And after that, we can use standard tools to obtain knowledge solvers from special solvers. That's it. Thank you very much for listening, and please read the paper.
Thanks for the talk. Thank you. Let's go to the next talk. The talk is the proof that generate efficient accumulation or folding for spatial sound protocols. This talk is given by Victor. Let's welcome.
Hello. Yeah, today. Okay, today I'll tell you about Protostar, which is a new generic recipe for constructing IVC schemes. And it turns out these IVC schemes are also incredibly efficient. And this is joint work with Benyi Chen, who's my colleague at Espresso Systems. So what is IVC? IVC is called incrementally verifiable computation. So imagine you have some iterative computation. So for example, say you apply a hash function to itself over and over again. It's referred to as a delay function. Or just think of any generic machine computation where you evolve the machine from one step to another, and maybe at every step you also choose exactly what instruction you're operating. And let's say we want to iteratively move the slide forward. Okay. Do I need to do something different? Okay. Well, let's say we want to make these computations verifiable. So we want to give a proof that we've evaluated this function, or we've evolved this function correctly from some starting point z0 to some endpoint zm, and this may be a non-deterministic computation, so there may be some additional witnesses that get input at every step of the computation. And ideally, we want that the proof is independent of m, so of the size of the computation. And this is called incrementally verifiable computation. It was first defined, and the first construction was given by Valiant in 2008. And the idea is that we have at every step not just the state of the computation, but also a proof, pi I, and we can update this proof along with updating the state of the computation. So the two properties that we want from IVC is completeness, which says that a prover, given the current state of the computation, so pi I and zi can evolve the computation, so update the proof. Importantly, completeness here is actually somewhat different from other SNARK completeness, which is that I don't need to know the previous steps of the computation in order to evolve the computation. So there's some sort of handoff property. And the other property is knowledge soundness, which means that I can, given the final output and the final IVC proof, I can extract all the intermediate steps and all the intermediate witnesses. So historically, the way that we've constructed IVC is from something called recursive SNARKs. So what I do is at every step of the computation, I prove that I've evaluated the function correctly. And additionally, I prove that the previous proof was correct. So as part of the circuit that I'm proving, I'm including the SNARK verifier of the previous steps of the computation. However, this has some downsides. This recipe works. It has some downsides though. And the main downside are about efficiency, which is that implementing this SNARK verifier can be very expensive, and it requires oftentimes it uses SNARKs that have a trusted setup when this is done in practice, and you require cycles of elliptic curves, which are hard to find. So this recipe is quite expensive. And fortunately, there's been recently a new recipe that has come up, and the core question that this new recipe answers is whether we can construct IVC without relying on SNARKs. And the answer, surprisingly, is yes. And this relies on something called accumulation or folding. So this idea was started by a work called Halo in 2019. And the idea of accumulation and folding is actually something pretty simple. So say we have two proofs. And what we could do is we could verify both of these proofs. But maybe what we can also do is we can batch these proofs. We can accumulate them together, fold them together into a single proof. And then checking this pi3 implies that pi1 and pi2 were correctly. And maybe there's some additional accumulation verifier that checks that this combining step was done correctly. And the idea is to not check pi1 and pi2, but reduce it to checking pi3. So a little bit more formally, these accumulation schemes consist of the accumulation verifier, which takes as input two instances to a relation, and the accumulation prover, which additionally takes as input two witnesses to the same relation. And then at the end of the procedure where the prover and the verifier, the prover might give a proof in additional some helper information to the verifier, we get a single instance out of it. And in the end, we have a decider. This decider may be much more expensive. You see the size of the boxes roughly corresponds to the efficiency of these things. So we want this accumulation verifier to be very efficient. At the end, there's an accumulation decider which checks the output of this result. But importantly, I can process this step, this combining step, over and over again before I use the decider. And this is exactly what is used when constructing IVC from accumulation schemes. So when I construct IVC from accumulation schemes, I'm not going to go into the details here, but the idea is basically that my recursive circuit now is not a SNARK verifier anymore. It's just this accumulation verifier, which checks that two statements have been combined into one. So we have really, really fast IVC schemes now from accumulation verifier. This is a very hot topic. And one of the interesting things is that I can define these accumulation schemes just from the discrete logarithm assumption with no trusted setup and no FFTs. So these things are very, very practical. Okay, it also turns out, so why are these so practical? Well, it turns out that accumulation is sort of easy. So let's consider a very simple example. Let's consider I have some sort of statement that checks multiplications. So just A times B is equal to C. And let's assume there's n of these statements. So let's also assume I have commitments to A, B, and C. And let's assume I have two of these things. So I want to check that A times B minus C is equal to 0, and A prime times B prime minus C prime is equal to 0. And our goal is going to be to combine these two checks into one check. So how do I do that? Well, what I'm going to do is I'm going to first add, an extra helper variable, mu equals 1, so that we check A times B minus mu times C is equal to 0. This doesn't really change anything because mu is just equal to 1. But in the A prime statement, we'll see later why this mu is useful. And so what we're going to do is we're going to define a linear function over A, B, and C, and A prime, B prime, C prime, and also the mu terms. So, and then we're going to evaluate the verifier function, so this multiplication, on this linear combination of these two proofs. So what happens then? Well, if we expand this, it's actually fairly easy to see that what happens is that this is V is a degree 2 polynomial, and we apply this to a linear function. So what we get out is a degree 2 polynomial. And if we check at the constant coefficient, this is exactly, just look at the colors, but you can also just see this yourself, that the constant coefficient is going to be exactly the V prime check, the V check over there, and the X squared coefficient is going to be the other check. So this allows us to then, and we know what we know what the result is going to be. It's going to be E, which is the result of this green check, and plus something in the middle. We don't really care what's in the middle, plus X squared times 0, which is the red check. So how do we build a protocol from this? Well, what we'll have is that the prover computes these CT terms, this middle coefficient, sends a commitment to them, and then the verifier will respond with a challenge alpha, and then we'll check this equation basically at a random point. And it turns out that if we do this, we get a new statement, A prime prime, B prime prime, and so on, and a new term E prime. And this basically is now a new statement, which we can just check by applying V to it. So what we've done here, it's okay if some of the details went over the head, but basically what we've done here is it's a fairly simple protocol for reducing two checks into one check. And also this reduction here is only linear in the red and green terms, so the witnesses, which means that if we have a homomorphic commitment to these terms, we can do these things over the commitments. So this is basically how these prior works work. So it works like Nova or Halo, they applied techniques similar to this, but they had some significant limitations. And one of the significant limitations is they only work for the so-called R1CS constraint system, which allows you to do additional multiplication gates. But what if I wanted to prove a computation that is more naturally expressed using higher degree gates? So for example, a quintic gate. And also there's some other proof systems that have so-called lookup gates. So for example, if I want to prove that some value is in some small range. Of course, I can always express these things using additional multiplication gate, but this may introduce an additional overhead. So ideally, we would have to do we would have a more native way to do this. Additionally, the most of the prior work do not support efficient circuit branching, which means that if I have multiple circuits, multiple instructions, and I want to basically select one of these functions at runtime, then the size would be basically the overhead would be linear in the number of functions. And yeah, so both of these things are very important for a lot of practical applications. For example, ZK EVMs, which is the idea that I can design a proof system for the Ethereum virtual machine. The other thing is that sort of on a more theoretical point of view is that all these constructions seem a little bit more ad hoc and they have different proofs. So it would be nice to have a unified and general framework. And that is exactly what we do. So we designed this very, very general recipe for designing IVC schemes, and it allows you to design new IVC schemes if you want to change some things about it. And additionally, it is also very efficient. It supports high degree gates, lookup, non-uniform computation, and the IVC proving cost is incredibly cheap. So the size of the recursive circuit is only 3 group exponentiations, and the additional prover cost consists of just committing to the witness. So 1 commitment to the witness. This is significantly better than any other SNARK system that you could use out there. So it has really, we're not talking about asymptotics anymore. We're talking about complete factors that are basically as low as you could hope them to be. So what is this general recipe? So the general recipe consists of multiple steps. So the idea is that we're going to build a very, first a multi-round special sound protocol for some relation R. So for example, this relation may be circuit satisfiability, and there's no efficiency requirements really. We have very few efficiency requirements for this step 1, which makes this incredibly easy. So for example, there's no notion of succinctness or anything that we need to. Then we can transform this multi-round special sound protocol into a NARC. This is very standard using the Fiat-Tramier transform. And then we have a generic and efficient transformation that basically builds an accumulation scheme and over the
We have this work. Our contribution is twofold. First, we formalize the concept of memory consistency check and the current constructions developed in the industry and prove their security in the PIOP model. And then our work also points out a new direction that may potentially lead to better constructions. Here is our contribution in more detail. The first part is the formalizing of the existing constructions. We note that all the existing protocols use the following technique. The idea is to sort the memory trace first by the memory address, such that the rows with the same addresses are grouped together. And then for the rows with the same address, we sort them by their cycle number, that is the row index in the original trace. As a result, in the sorted memory trace, every row depends only on the previous row, so the history dependency is eliminated. So we propose the sorting paradigm that captures all the existing constructions, which works as follows. First, the prover sorts the memory trace and gets the sorted trace and sends the sorted trace to the verifier. Then the verifier checks that this sorted trace satisfies the memory consistency constraints, which can now be captured by a simple vector equation because the history dependency is eliminated. And then the verifier checks that this the old trace and the new trace are indeed permutations of each other. And finally, as a final step, the verifier checks that this new trace is indeed sorted first by the address and then by the cycle number. This is the most expensive part of the memory consistency check, and this is also where the solutions of the different leaky VMs differ from each other. Next, I will present three different protocols that deal with this last step, and respectively for three different memory models. The first model is also the simplest one, that is the contiguous read-only memory, which is adopted by the carrier virtual machine developed by the Stockware company. So this model requires that all the addresses ever touched by the program during the execution must form a contiguous subset of the final field. As a result, after sorting, the address in the sorted memory trace must satisfy that the address in each row is either the same as the address in the previous row or increments by one. Another property is that because this model requires the memory to be read-only, so there's no need for the opcode because they're just all reading, and there's no need to check the cycle number. It's not sorted by the cycle number because all the rows with the same address are just the same with each other. So the memory consistency check for this model is very simple and thus efficient. However, this model is very restrictive and very inconvenient to program for. The second model, which is also widely used, adopted by almost all the KVM projects, that is read-write random access memory with 32 bits memory address. And however, it is also most expensive because it requires a 32-bit range tag. And that is currently implemented by 2 lookup arguments. And if 2 lookup arguments does not sound very expensive, consider even larger memory spaces. For example, 256 bits. That will, for every 6 bits in the memory address, you need to pay another lookup argument, and that makes it very expensive. So this is the second model, and the last model is also read-write random access memory, but with full address space, which means you can use all the elements in the final field as memory addresses. This is proposed by Triton VM, developed by the Neptune company. And as far as I know, it's also only adopted by this voting machine. So because the final field usually is 256 bits large, it usually suffices to provide a very large memory space. And the challenge for this memory model is that it's hard to check or to even define what it means for the address column to be sorted. Because we can't just take two field elements, take their difference, see if the result is negative or positive, and decide if one element is ordered before the other, because now all the field elements are in our consideration. We don't have a negative number, such thing as in the final field. To deal with this problem, we note that we actually don't need the address column to be sorted. What we really hear is that all the identical addresses are grouped together. So that's why Triton VM develops this contiguity check for checking this property of the vectors sent from the program to the verifier. So here are the three memory consistency checks that are already developed in the industry. Here's a summary, a short summary, and a comparison between them. Now it's time to introduce our new method for dealing with, for building the memory consistency check, which we call the address cycle method, which provides a better way to eliminate the heterodynacy property of the memory. So the basic idea is still to make the identical addresses adjacent to each other. Intuitively, the sorting paradigm achieves this by reordering the trace. This is somewhat heavy because the prover has to send a sorted copy of every column in the memory trace. In comparison, our method also makes the identical addresses adjacent to each other, but we achieve this by redefining what it means to be adjacent. This is more lightweight because the prover only needs to send a single vector that represents the information that encodes all the information for describing the new definition of the adjacency. In more detail, we introduce a permutation called denoted by sigma that points every position in the address vector to the previous position where the same address appears. And for the first position, this permutation points it to the last one. And so it forms a cycle, and all the positions of the same address are in the same cycle of the permutation. And intuitively, the memory consistency check is equivalent to checking that for every arrow here in this permutation, we need to check that the memory value vector has the same values in the two positions connected by this arrow. Of course, we don't need to check all these arrows because first we introduce a new vector called the first vector for marking all the positions where the address appears the first time. And for the other positions, we just fill it with 0. Now note that if an arrow starts from a position where the opcode is writing, or the arrow starts from a position which is marked by the first vector, then in either case we don't need to check that the values connected by this arrow is the same. And so in the end, the memory consistency check is equivalent to saying that for all the green arrows here, the memory values connected by these green arrows must be equal to each other. And in this very simple case, for the address A2, we only need to check that B5 and B8 are the same. So based on this new point of view on memory consistency checks, we developed a memory consistency check called PROMAM, which involves one vector equation and one permutation check, which I will not explain the details. The challenging part of this protocol is to check that this sigma permutation and the first vector, which should be created and sent from the prover to the verifier, they are consistent with the address vector, which is also sent from the prover. So to solve this challenge, we know that if the sigma permutation and the first vector are both correct, then then they should have the following properties. First, by the definition of the sigma, it always points a position to a previous position. So for almost all t, sigma t should be smaller than t, except in the corner cases where this position is the first time this address appears. In that case, only in that case, sigma t is greater than or equal to t. So that's the first property. And the second property is that also by definition of the first vector, which marks all the positions where the address appears the first time, and address can only appear the first time at only one position. So for all the positions marked by the first vector, all the addresses must be distinct from each other. It turns out that these two properties suffice to guarantee the correctness of sigma first vector, which I will not dive into the proof. So to check the two properties, for the first property, we just use one lookup argument, and for the second property, we developed a new protocol called distinctness check, which is a generalization of the contiguity check developed by Shorten VM, and I will just skip all the details because of the time limit. And finally, as conclusion, let me compare our protocol with all the existing protocols. For efficiency, of course, the contiguous ROM memory, because it's very simple. It's the memory consistency check for this model is the most efficient, but is also the most restrictive in terms of functionality. And our protocol is improvement in efficiency side to both of the other two protocols, and our protocol also supports the full memory space. That's all. Thank you.
Thanks for the talk. Any question?
Which page? Second. System model.
At the beginning, the program should be, I don't know, just not transformed as a virus, and it should be sent to the verifier.
You mean this?
Yes. What is the wild virus? There is a hash value or
No, it's considered a summary of the program. It is probably polynomial commitments that encode all the information of the program. For example, its instructions. If you just use non-structured digest hash function, it will be very hard for the verifier to exploit to use.
so types to in this program here. I mean, the output should be output by the VM, and it should be sent to Wi-Fi.
Yeah, the proof should be sent to the verifier. Yes.
Yes. So the text here will join the verification.
Yeah, here's the trick. The verifier must know the program somehow to know what it is trying to verify in the first place. And there are two kind of solutions to this. First, the verifier just reads the program itself. And in the case that the program can be very huge, the verifier is supposed to be succinct. Alternative way is to just compress this program in a cryptographic way, such that and the verifier reads this a summary of this compressed version of the program.
Any other question? Okay.
I'm wondering, like, the polar program being
current system and so forth.
The current system in the construction of the memory, the logical memory space is just as large as the final field, for example, 256 bits. No, but I know it's, of course, you can't, this virtual machine cannot be run on the actual machine that is a machine that actually has this large memory. It's, of course, the host must simulate this memory space point.
It has to be much larger.
And no, the host does not need to use this much memory. It only copies the actual memory that is used by this guest program and simulate it using a binary tree or something.
Okay. Any other question? If we have no question, let's thank the speaker.